All right. Hello, everybody. Today we will be talking about networking, and you will learn to love it. That is a promise. It's low-key kind of buns, but that's all right. So this week we're on week 3 of boot camp. We still need to fix that, so it says 1 to 4. But yeah, so today again will be introduction to networking. And hi, I'm Nat. I'm a cyber defense and engineering consulting intern. This year, I'll be your co-captain. Last year, I was the captain, and the year before that, I was the networking lead. And I've done networking for all 2 and this upcoming year as well. I'm a fourth year CS student, and I really love frogs.
What's up, everybody? My name's Adam. I'm an IST Systems Administrator intern at Esri. This year, I'll be our co-captain and Linux lead. Last year, I was our Linux database lead. I have a bachelor's in CS with a minor in cybersecurity. This year, I'll be starting in the MSIS program, which is Information Security. I also have my Sec Plus and Network Plus certifications. And I'm really into this game called Slay the Spire. I got a screenshot at the bottom there of me doing something really fucking stupid. Anyways, today we're gonna be starting uh, intro to networking, and then we're gonna go into competition networking and client server model, firewalls, and then we're gonna kick off with our lab. Um, you guys will be needing your VPN accounts at the end. Yeah,
And SDC.
and SDX and SDC accounts. Yeah.
All right, so let's start with introduction to networking, and this is not the LinkedIn or the social one. So first, what exactly is a network? It's essentially a system of interconnected network devices. And those devices work together to communicate and share resources with each other. So for example, a network is us right now. So we are able to talk to you guys and you guys are able to talk to us. And we're also able to share resources like food or water, at least with the people in the room. Definitely not online. Yeah. And then going into networks and devices, this section is just going to talk about different devices on a network. And any device on a network contains at least one network interface card or NIC. And this can be a wired or wireless connection that allows you to have access to a network, such as the internet. And you have things called network devices, which are like routers, switches, and modems, and that helps kind of manage your network traffic. Then you have things called end devices, which are at the edge of a network, and that is oh no, I just saw it. And that's anything that can send or receive information. And those are computers, phones, servers, and etc. I'll edit that slide later. So the section about topology, it's going to be these upcoming 2 slides. It's quite a lot. So if you have any questions, yeah, please just let me know. I will take a stop somewhere for questions. So what exactly is a topology? A topology is a fancy term for a network document, and it kind of maps out the different devices that you have and any of like the network traffic and how that would work and move around. So for example, in this topology, you have everything on the left before the firewall. That, in this case, we can conceptualize that as a LAN or a local area network. And that's just like a smaller network that you are a part of. And in this LAN, you have 2 workstations, a web server and a file server, as well as a switch. Then you have a firewall that is in between the switch and the router. So it kind of separates you from the outside or the WAN, which stands for Wide Area Network. And yeah, those are just 2 types of networks, it's more of a conceptual thing rather than a concrete thing. But you can pretty much be connected to as many networks as possible. You're not limited to just two. This is kind of a basic topology, but it's more realistic for a company. So we have everything on the left of the firewall, which can be like a development or a testing and staging environment, whereas everything on the right is similar to a production environment. And the things in the production environment, they go live into the real world, which is connected to the internet. And having that firewall there is really important so that you can't really have anybody touching your testing or your development areas because that's just kind of not good in general. Yeah, but as you can see here, you've got two routers and they help manage the traffic from the internal or like the development side on the left and anything with the outside, or in this case, the WAN on the right. Are there any questions in the room or online? Do you actually?
Switching around.
Oh yeah, I just wanted to know what's the difference between a switch and a router.
What a lovely question. A switch manages traffic in between devices of a specific network or the network that you're on. So as you can see with switch one, it's going to manage the traffic for, I think that's a modem, the printer, person one, and the other switch. But the router is going to manage traffic between different networks. So as you can see here, router one is going to manage the traffic between, in this case, the LAN or like the dev side and the WAN or the prod side. Nice. Anybody else?
Layer 2, layer 3.
Oh, do you want to talk about that?
Yeah, so another difference between a switch and a router is that switch deals with layer 2.
Layer 2 switches deal with layer 2.
Yeah, layer 2 switches deal with layer 2. Layer 2 is basically your data link layer of the OSI model. We're not going to cover the OSI model because it is typically covered in class, or you can just search it up online and it takes a lot of time to explain. But that's typically data link layer is dealing with MAC addresses, which is like a bunch of hexadecimal characters. It's ugly for sure. And then layer 3 is usually your router, and that deals with your IP addresses. So, your 192 wants to say blah blah blah, whatever. Yeah, I just wanted to add that.
Yeah. Oh, what's the difference between a managed switch and an unmanaged switch? To be honest, I'm not really sure. Oh, thanks.
Yeah, so managed switch and unmanaged switch, those are definitely different in price. Another thing is unmanaged switches, you never usually don't have some kind of management interface. So unmanaged will typically just work basically on its own. You won't have to touch anything on it. And a managed switch, you probably have to configure your own like firewall rules or hit port switch. Is it port switches or like turn enabling and disabling like ports on
Security?
Yeah, it's just like if you're using it or not. So like in enterprise, usually you'd have managed switches where you configure your firewall rules and stuff like that. And then whenever you have a switch that's not being used, you should disable it just so that no one can attach anything without your knowledge. Yeah, and another question.
The question is, how does this topology work with VPNs? So if this is like a work environment, you would have, I'm pretty sure you would have something called a VPN server. And that pretty much gives you, it will host a VPN on there and you will get the VPN profile and connect from it from like the laptop on the top left. And having that VPN server inside of the infrastructure pretty much allows you to have access to the resources on that infrastructure once you connect the VPN. Okay, I'm gonna move on. Oh, how difficult is it to make your own VPN server? Depends on the VPN, but yeah. Yeah, it depends on the VPN, I would say.
We haven't set up any, so I would.
We've set it up during practice before,
Oh yeah.
but yeah, I think it's not that bad actually. Yeah. All right, moving on. So now we're gonna go into a lot of talking about different vocabulary and what they are. And hopefully we can kind of conceptualize this a little better if we think of everything in as if they're in a neighborhood. So an IP address is a unique identifier that's like an address for a virtual machine, or not a virtual machine, but for a machine virtually. It helps identify the machine on the network rather than like a physical address that is a MAC address, but we're not going to go into that. And then we have a subnet mask, and this helps define the different parts of an IP address, which are the network ID and the host ID. And we're going to go a little bit more into that later. Then we have a router, and as mentioned before, a router helps manage traffic between different networks. And you can have as many networks as you would like, assuming you are able to have that many connections. And a default gateway is the path that allows you to connect from your local network to an external network. So most of the times, or all of the times, this would be the IP address of your router, but specifically it will be the internal IP address of the router. Then we have a service, which is very important in terms of CCDC as a competition. And these are just software apps or different like runtime protocols or processes that run on your machine and are hosted on your machine. So some examples of this are like a web server, a file server, or remote access protocols like SSH or RDP. And in the competition, these are scored most of the time if it's shown on the scoreboard. Then we've got a protocol, and we have two important protocols that we will be talking about later. And this defines how the traffic is going to move between a sender and a receiver. Next, we have port. A port is a connection on your machine that is tied up with a service. And it pretty much, you have something called an ephemeral port, which we'll talk about later as well. But yeah, ports are really important to learn about because they can help you determine how to block off your traffic or how traffic might be traveling or where traffic is traveling to. And an interface, as kind of mentioned before, it's what allows you to have access to a network or the internet. And firewalls are really cool. They allow you to control your traffic, the traffic of your network. So you can define who's able to access your resources, whose resources you're able to access as well. And so I know all of this was a lot, but if we want to think about this in terms of a neighborhood, you could say that the network you're on is the entire street. And the subnet or subnets are several different blocks, which split up the street into smaller parts. An IP address is the IP address of your house. And the subnet mask helps separate your house address into the number portion and the street portion, where the street portion is the network ID and the number portion is the host ID. The router helps manage traffic, so I was gonna say that's like a traffic light or a stop sign because it manages traffic between different networks. So if you have like two perpendicular streets, the traffic light or stop sign will manage that. The default gateway is how you're able to leave to the outside world. So that would be your door, like the main entrance to your door. A service is like, what's the purpose of your house?
Yeah, kitchen. Yeah, like a living room,
Yeah.
stuff like that.
Protocol is how the traffic works. That's just like, oh, are you going up and down the street in a car, bike? Are you walking? A port is like a room in a house where every room has a different purpose. So different ports have different purposes because they're associated with either services or they're ephemeral. An interface is what connects you to the outside world. It's not your door, it's going to be your doorway or any hole in the wall that allows you to escape, really. And a firewall is like a fence, or if you're really cool and fancy, security, walking around the perimeter of your house to make sure nobody can go in. Yeah, I know that was a lot of words. Do you guys have any questions? All right, epic. So now going more in depth with IPs and subnet masks. So an IP, and we're going to be using IPv4, which is a 32-bit long identifier of a device. So an IP address is split into 4 octets, where each octet has 8 bits, hence it's called octet. And a subnet mask, as stated before, is able to separate this IP address into a network ID and a host ID. So the network ID, pretty straightforward. It's the ID of your network. And the host ID is the ID for a machine on that network. So in this example, if we have the IP address of 192.168.1.100, the subnet mask is 255.255.255.0. Because 255 is the greatest number that you could have for an octet, the numbers ranging from 0 to 255. Because the first 3 octets are all filled out, that means because they are all 255, it means they're full. So your network ID is going to be 192.168.1, and the last number is going to be 0 for general practice. Not really going to go too in depth in that, but yeah. Then the host ID is going to be the last octet because it's an empty octet in the subnet mask, and your host was going to be 0, or it's going to be 100. Are there any questions on that? Yeah, yeah. Anybody else? Yeah. Oh, yeah. Yeah.
Wait, when would the default gateway not point to the router, or does it always point to the internal IP of the router?
I'm pretty sure it will always point to the router because your router is your way out. I think maybe it might point to a switch, but I think most of the time it will point to a router. Yeah, I'll get back to you on that. Anybody else? Okay, cool. Now we're going to talk about competition networking, or what networking looks like in a competition. Oh,
Option work needs to work. Okay, to the switch. It's a good point.
yeah. Somebody in the Zoom said that in order for ARP to work, they're pretty sure it needs to be connected to a switch. Yeah.
You want to go over what ARP is?
Oh, look, you don't. No, it's
So
fine.
ARP stands for Address Resolution Protocol, and it basically translates between your MAC address and your IP addresses. So, so when your traffic goes to a switch, you got to know like, well, where does it go? But obviously your switch deals with layer 2, so then you have to translate it from MAC address to IP address, so then you can get out. And it also when traffic's coming back in, the switch has to tell, or it's got to like tell where the traffic is supposed to go. And that is basically translating ARP the other way. Yeah, that's a good point too.
All right, so this is the topology for the competition. In the blue or the cyan box, you have your pod network where that each team will have. And in the yellow, you have the core network for like the overarching, not infra, but the overarching networking of the competition. So I'm going to start in the pod network and then move over to the core network. And it's changed actually recently. So it's not exactly the same. There's a little addition to it. So in the pod network, which each blue team has, you've got your blue team servers that you're trying to defend and secure against the red team. Then that is connected to your pod router, which is what gives you access to the internet and access to the rest of the networking. And the pod network is your internal network, and it can have an IP network of like 192.168.1.0, but we've also seen it as no, yeah. It's been 198 or 192.168.1.0. Sometimes the numbers change a little bit, but that's usually what it is. Then moving on into the core network, which can have an IP of 172.16.0.0 or 10.100. Yeah, or a different network ID depending on which team you are. So this comprises of a scoring engine, which is what gives you your scoring for your services. And that pretty much sends like requests to the blue team servers. And it's like, hey, is the service working? And if it does, you get points. If it doesn't, you might not get points. And if you don't, if that service isn't able to return the request after 5 attempts, you'll get something called an SLA or a service level agreement. And once you get SLAs, that's when you start losing points. Also attached to the core network is the red team. And yeah, having red team and the scoring engine together on the same network is pretty interesting because you aren't able to block off a specific IP because they do rotate IPs around. So you're not going to know if it's a scoring engine trying to request your service or if it's red team trying to hit you and take you down. And attached to everything is the core router. And that helps manages all of the pod routers and gives them internet, as well as managing the scoring engine and the red team from also allowing them access into the pod networks.
Could you explain what /24 and /16 are at the end of the IP addresses?
So /24 and /16 it's CIDR notation for a subnet. And I didn't go into this, but a subnet pretty much divides up a network into subsections. So this kind of helps manages This goes in hand with the subnet mask and helps identify which part is the network ID. So in the /24, it means the first 3 octets are going to be a part of your network ID. And with a /16, that means the first 2 octets are going to be the network ID.
Counting bits.
Yeah, as Adam said, it's counting the number of bits that you have. Did you have?
Oh, I was gonna ask, how do you tell whether it's a scoring, oh, sorry. How do you tell whether it's the red team or like you mentioned, the scoring? Engine?
Yeah, you can't really tell because they both rotate IPs. I think maybe if it's red team, you'll be able to see logs of like failed logins. But sometimes that can also happen with the scoring engine if you've rotated credentials and suddenly your passwords don't match what's in the scoring engine anymore. But yeah, it's a little difficult to tell.
So yeah, like in the past, this topology has changed. It was different. It was smart for teams to just block off the red team if they somehow identified their subnet, and then you would just get your scoring traffic, and then that would be you just keep getting points, and red team would never be able to hit you. So that was before, and now they changed it so that you can't tell. The IPs of the scoring engine and red team change frequently, so you can't exactly, lock down who's red team and which one's the scoring engine and stuff like that. We have a question here in the chat. Were there any ways you could identify in the past some patterns? For prior experience, we did notice like checking logs is a big help. Like if you notice someone's trying to log in with an account that is not being scored with SSH or something, that could be a big tell.
The process IDs, netcat, netstop.
Yeah, if you check your processes and your open ports, if you notice there's like anything strange, sometimes you can close those vulnerabilities, but yeah, those are just some of the patterns. There's definitely always new ones that we don't notice as well. But that's a good question.
Yeah, and as I mentioned at the beginning of this, there's a new addition to the topology. Every team now has, at least for the Western region, they now have a VPN server inside of their pod network. So what that means is instead of having to go through NAT, which I will talk about next. That's crazy. Instead of having to do that, you can have internal access to your network using your host. So that means if you're like on your personal device that you're using to connect to the competition infrastructure, you can go to all of your internal resources, like hit a 192.168.1 whatever web server. You are able to do all of that. You're able to ping using your own terminal instead of having to ping with the NATed IP. But we're going to talk about NAT anyway because I don't care. So NAT stands for Network Address Translation. And there's 2 types of NAT. There is one-to-many NAT, which is here, and there's one-to-one NAT, which is typically used in competition. So one-to-many NAT is built to conserve IP addresses by translating multiple internal IPs into one external IP. And this is kind of how networking works in reality, where, for instance, if you have, like using this example, if there's a web server with an IP of 192.168.130 and a file server with the IP of 192.168.115, you could hit them both using one address which is 172.16.30.144. But how exactly are you able to differentiate if you're going to hit the web server or the file server? And what comes into play is something called PAT, or port address translation. And that pretty much assigns a unique port number to both of the web server and the file server. So when you hit a specific port, it will take you to a web server, but when you hit another port, you can hit the file server. And if I remember correctly, this is how networking works inside of your homes. So all of your devices get translated to one public IP by the end of the day. And you will have different ports to connect so it can send traffic back to the right device. Oh, sorry.
So if you were to hit this IP, you would essentially take down all the devices that are connected to this router, or is this a switch? Router, right? Yeah, all the devices though? Or how does that work?
I think I don't actually know for sure, but because none of them have a port associated with it, I think it's just going to be confused. Yeah, I can get back to you on that. No, yeah, good question. All right, I'm going to move on to one-to-one NAT. This is my favorite NAT for working on labs because it makes everything so much nicer. And this is also called static NAT because it's a direct translation between different networks. So in this example, you have two networks. You've got your internal network of 192.168.10/24 and another /24 network, which is 172.16.30.0. And what this does is the only part that changes is your network ID. So your host ID will stay the same because you're kind of on the same network, you're just changing them. So your host will be able to be identified by whatever it is, such as 30 and 15. The only thing that's changing is your network. So this time, when you want to hit that web server, instead of going to the same IP address as the web server, you just need to change the network ID to match 172.16.30 and keep the same host ID, which is the last octet, and in this case, it's 30. And the same thing happens for the web server, where you can hit 172.16.30.15.
Just something to add here. A lot of the times when we're troubleshooting, it's important to be aware of where you are in the network. So if you're internal and you're trying to access a web server, you would use the 192.168.1 network here listed on the left. But if you're considered outside, then you have to use the external network, which is the 172.16.30. And that difference is really important because if you're outside and you try to use the internal one, your router basically gets confused, and you won't be able to access it. Yeah.
Yeah, adding on to that, sometimes everything looks right internally, but when you're trying to see what it actually looks like, you might need to use the NAT IP instead, and you'll see like, oh, I think my web server is up. Why isn't it scoring? Because you're looking at it internally, but then once you hit it externally, you have an empty page. So that's why it's not scoring. Yeah. Moving on.
All right. So now we're going to talk about the client server model. Before in the terminology slide, this was about like the protocols. There's two types of protocols. Actually, I'll first go over the client server model, but basically this is kind of like a restaurant where the server is the restaurant and the client is someone going to that restaurant or a customer. You're basically providing a service, and the client is going to that service. Yeah, I can do this. No, I can just go to the next one. Yeah. So what are ports? So these are numbers that identify, along with an IP address, which network socket to connect to on a given device. So some common port numbers and associated services are ones, or these are the ones that we commonly see in competition. It's important to recognize whether it's TCP or UDP, which I'll be talking about later. But some common ones are 20 and 21 for file transfer protocol. Your port 22, which is secure shell, which is what you guys researched in Business Week. TCP 25, this is simple mail transfer protocol. UDP 53 is domain name services or server. TCP 80, your hypertext transfer protocol. And then 443 is your HTTP secure and stuff like that. As a pop quiz, does anyone remember the port for RDP? We did this research. What was it? No. I guess someone else? That's close. Anyone else? No.
Anybody?
Anyone online? Over here? 389? No. Close? Raymond got it online. 3389. That's correct. Yeah, it's definitely confusing. So you were kind of close. You're missing one number. LDAP is 389. LDAP secure is 636. But RDP is, yeah, 3389. They do get, you might get confused because it's just one number difference for 3389 versus 389. But yeah.
This is just something that you will get better at with practice. Like it took some time to recognize these numbers and what they mean before actually understanding and associating services with them. But yeah, so you mentioned a socket earlier. What is a socket?
A socket is kind of like a pairing between an IP address and a port. So it basically tells you how to connect to the service. A service might be hosted on the certain ports, like 25, 53, the ones that we listed here. But then you have the socket is like that pairing with the IP address. So when you're hosting a service, like let's say a web server on HTTP, then you have the IP address of the machine hosting it with the port, and that's basically a socket. I hope I gave a good enough explanation. So now we're going to talk about TCP and UDP. TCP is slow but reliable and uses a connection. This is definitely better for the services that don't rely on speed but want to be very reliable, and you don't want to have like data loss or packet loss. It uses a TCP handshake and also has features like synchronization and flow control. And on the other hand, we have UDP. This is extremely fast, but unreliable because it doesn't have any error checking and there's no acknowledgements, and it just sends data kind of like spitballing at the destination and just hoping everything gets there.
So just to add, because technology has evolved over many years, UDP has become more reliable now.
Yeah, so just some examples, like if you're gaming, you might want to use UDP because that split-second difference might matter. But if you're like handling sensitive information, you might want to use TCP because that is definitely important. Someone said, pretty sure Google uses QUIC, which is built on top of UDP. I've never heard of that.
It's pretty neat.
That's pretty cool information though. Thank you. Now, and this is kind of like a model of how it works. So on the left, we have the TCP handshake, where the sender first initiates this connection by sending this in, and then the receiver sends back the SYN ACK, kind of acknowledging, okay, we can communicate now. And then the sender sends an ACK and just basically acknowledges the SYN ACK. And basically that's the start of the connection. And then from there, the sender can start like communicating with it. But on UDP, it's just like sending back and forth, request response with no form of reliability or anything, no checking. But any questions so far on this client server model in TCP UDP? Good. All right. So now I'm going to talk more about sockets. At each end of the connection is basically a pairing between an IP and a port, kind of like I mentioned before. This is kind of where we talk more about ephemeral ports. At the bottom left, we see like port 57,138. And on the right, it's just 80. And 80, as we've seen before, is HTTP. So the right side is our server and the left side is our client. And ephemeral ports is a really high port. Ephemeral basically means temporary. But it's a temporary port used by the client to communicate with the server without like conflicting with anything on the lower ports of the client. So that kind of as a pop quiz, who knows how many ports there are? It's a really high number. No. Close. 65K something. Yes. Anyone know the exact number? Yeah, that's purple chicken. That's correct. 65,535. That is correct. This is just something you don't have to know. It's just cool to know. But yeah. So why is this important? This is important for analyzing your network traffic. And you can identify normal and abnormal traffic, and then you can tell if it's coming from the scoring engine or orange team or red team. This is a little more difficult to tell just based on your network connections alone. Sometimes you can list processes in this command below, but it definitely helps you troubleshoot services. Like you can tell, is my service actually listening for something, or is it just is it disabled, or is it being blocked by a firewall? So like an example would be like we run this netstack command and we see that our web server is hosting something on port 80. So we're good on port 80 and we know that the service is running. But from the outside, my client can't connect to the web server. So then you check your firewall rules and you realize I'm blocking port 80. So that's why, even though it says you're listening on port 80 in your connections here, active connections, your firewall is still blocking it, and that's why it can't connect. So that's just an example of troubleshooting. You can see an example of like your ephemeral ports under local address. You'll see like really high ports towards the bottom. And your foreign address will usually be the server that's hosting whatever service. And then the state is also important. It says listening here, so you know like a server, if its server is hosting a web server like port 80, then you'll see that listening status. But if your client is connected to the website or like just looking at the website, you'll see an established state. Yeah. And then you can see the protocol on the left side as well. Sometimes you might forget to list both TCP and UDP connections and only look at TCP, but sometimes it's important to look at UDP as well. Some services do use UDP, just as a heads up. So as a review, we covered TCP and UDP, connectionless and connection full and connectionless. Yeah. And then there's ports, numbers that identify running service or application. And then you have sockets, of course, which are your IP and port mapping or pairing. And then you have your source and destination addresses/ports, which is basically the sockets that we're talking about. And then ephemeral ports, again, the really high ports that your client uses to connect temporarily to your server. And oh yeah, we just mentioned sockets, but moving on to firewalls. Yeah, it's not a waterfall or water wall. So the main purpose of a firewall is to block IPs, control your traffic, block ports, and basically filter your traffic, ingress and egress. So I'll start at the top here. It just blocks, in terms of blocking IPs, it can block a whole subnet or an individual IP. It depends on how you set it up. You can also block specific ports. Let's say you don't want anything to connect to like a database or something, then you can block it off like that. And then for filtering ingress and egress, basically ingress means like coming in and egress means going out. Ingress filtering is pretty important when you're dealing with a red team. You don't want to have all your ports open, or else they might have like a beacon or something listening that you're not aware of. So blocking off only or everything besides the ports that you need is very important. And egress, usually not dealing with that too much, but it can be important for kind of managing your network traffic. Yeah, the rules in CCDC have changed. I don't think we're allowed to block outgoing traffic, are we?
As far as I'm aware, we're not allowed to block outbound on workstations.
Yeah, that's interesting. We haven't seen that enforced that much, have we?
It's been enforced.
Oh,
I think you get penalized.
you get penalized if you don't do that?
Yeah,
That's crazy.
Yes.
Okay. But going into host firewall versus network firewall. So a host firewall is basically a firewall that's hosted on your computer or host, and it filters inbound and outbound traffic for a single device, not your entire network, just with just the host that it's on. So you have usually two different rule sets. Rule sets like inbound, outbound. Yeah, like inbound, outbound. On Linux ones, you usually have three different rule sets. You have input, forward, and output. And Windows.
For example.
Oh yeah, an example is a Windows file server having a Windows Defender firewall. That's an example of a host-based firewall. There's like domain, public, private,
Oh yeah.
but that deals more with like GPOs, right? But anyways, I digress. So network firewalls is filtering stuff throughout the network, and you can do inbound and outbound you can filter inbound and outbound traffic for both your internal side LAN and your external, which is WAN. 4 different rule sets.
Yeah. LAN, two for LAN, two for
Two for LAN. Oh yeah. So you have two for LAN and two for WAN, inbound and outbound for each of those. So an example would be a network has a Cisco Firepower firewall, or an enterprise you might use like Palo Alto firewall solution. So yeah, in the bottom there's like pictures. The left one is just your host, and then the right one is your network firewall. It's kind of hard to see, but that brick wall in the kind of in the middle of the diagram is represents the firewall. Another important concept is stateless versus stateful. So when a firewall is stateless, it means it uses an access control list, ACL. I believe that's what it stands for. Yeah. And it looks at every single individual packet and compares it against the ACL to see if it matches any of the rules. And if it does, it'll let it through, usually. And for stateful, it pays attention to what connections different hosts have established with whichever host that the firewall is on. And if it is already been connected, it'll just let whatever traffic through. So stateful keeps track. I think it uses a table, right? To manage the connections.
No.
Yeah, I'm pretty sure it uses a table to keep track of which connections have been established. But this is just, stateful is typically faster because it just lets us through if it recognizes the connection. And stateless has to check down the list every single part of that ACL.
Adding on for stateless, if you want to block it, like for example, if you're crazy and you want to block every single port of an IP or very specific ones, you would have to block it every single time it wants to make a connection. I'm pretty sure. Because stateless firewalls really only care about the destination. They don't care about the journey and trying to remember everything.
And another thing, ACLs, as I mentioned, it goes down the list. So whatever, it starts at the top and goes all the way to the bottom. So if you somehow messed up the order of your rules on the ACL, you could end up blocking the entire all of the traffic basically instead of just some. So usually you have what's called an implicit deny. And the implicit deny is usually placed all the way at the bottom. So if something doesn't match any of the rules, it'll just get blocked by default. And that is very important. Is it possible to combine both a stateful and stateless firewall? I don't believe so. It's usually either or.
I think so, yeah.
I don't think we've seen any situations where it's like combined.
Yeah, and like even when we're on the Alpine, when we make it stateful, it just remains stateful anyway.
Yeah, it's usually like either or. Would stateless be more secure than stateful? I guess so. I guess it would be more because you have to check every time.
It's just not efficient.
It's just not efficient, right? It's slower. Stateful helps with speed because you're not checking every single time, but just like pretty much the first time when you establish the connection. And after that, it just lets the rest in. But if somehow something gets compromised between then, I guess that would be the insecure part of the stateful. But we had a question?
Can you give examples for like one of each? Like what type of environment you would use stateless for versus stateful?
Yeah, sure. So examples of when you would use stateless versus stateful. Stateless is when you don't trust anything on the network. Uh, sometimes you're working with firewalls that are just stateless or stateful by default. An example would be like Windows Defender Firewall. I believe that is stateful. Yeah, stateful. And then on the other hand, when on the Linux side, our commonly used firewall is called IP tables, which we'll go into later. That is a stateless firewall. And you can make it stateful by setting specific rules in your ACL for that IP tables list, but by default, it is stateless. That's a good question. Very good question. Any other questions? Okay, I'm gonna move on. Yeah, we got that question. Yeah. So now I'm going to talk about next generation firewalls versus traditional. This is not extremely important to understand because a lot of times we're just using traditional firewalls. This is just kind of like the future of which is called next generation firewalls. So next generation firewalls are stateful and they have comprehensive application control and visibility. So a lot of them are easy to install, configure, integrate security tools, and like they reduce administrative control. So you don't have to do as much. So it's a lot more modern, but at the same time, like can come at some kind of disadvantage. Also, SSL traffic can be decrypted and inspected. So this is like kind of like integrating what's that? Yeah, kind of like certs to understand like encrypted traffic. And yeah, at the bottom, IPS and IDS are integrated. I was about to talk about that. Intrusion prevention systems and intrusion detection systems are basically ways to control and monitor your traffic. If anything like out of the ordinary or abnormal comes across or is kind of trying to enter the network, it'll recognize that, and prevention systems, IPS, will stop it there and make sure it doesn't come into the network. And IDS, intrusion detection systems, will just notify you. So there's a difference there. For traditional firewalls, like we've talked about, they're typically stateful, incoming and outgoing traffic, and then usually have some kind of partial application control and visibility only kind of tooling. And they also have security tools to kind of manage it. And these are pretty pricey because you have to pay for like enterprise subscriptions and stuff like that. I worked with a Fortinet firewall at home, and like all of the subscriptions and tool and like features are blocked behind paywall. But it does work functionally as a firewall just on its own. I believe it's the same for Palo Alto and a lot of the other firewall appliances. And this cannot decrypt and inspect SSL traffic as far as I know, but and typically you have IPS and IDS integrated separately, so you don't have it directly on the firewall, but it is an appliance in line or out of line, so that you can still have that functionality to block abnormal traffic. Any questions about this? I believe they cover next generation firewalls and Network Plus, but I haven't seen any of these at all. So here's an example of a firewall, kind of like as an illustration. So inbound, if you only allow you usually want to only allow required services and allow certain subnets and IP addresses so that you control what kind of traffic is going in and out of your network or in. And then outbound is usually block everything. This is an example of breaking the internet is like
Blocking everything will break the internet.
yeah, blocking everything will break the internet. So you want to make sure like you don't block everything, or else even if you have traffic going in, you can't have anything going out. So um, something that we ran into with IP tables, because it is stateless, if you like forget to put your stateful rules to make it stateful instead of stateless, and then you block outbound, it's like
That is combining stateful and stateless.
what? Like
Having one of them be stateful, one of them be stateless. And you guys versus.
I guess so, yeah. So I guess going back to Purple Chicken's question is like having a combination of stateful and stateless. If you set one chain in your IP tables rules to stateful, I guess that is kind of a combination because the other chain is not. I guess that's a good point. Yeah, but kind of going back, if you have traffic coming in, but you block outbound, you're not going to get anything, even if you notice like, oh, I don't have any firewalls for inbound. How come I'm not able to access or go out to the internet and stuff like that? So you got to pay attention to both inbound and outbound firewalls. This is an example of a pfSense WAN firewall rule. This is just if we look at each column here, you can see the protocol is IPv4. Your source is 172.16.109.39. The star under port, destination, port, gateway, all that means anything. It'll allow anything. And then usually you don't really set like queue, schedule, description. The description is just like notes. And then there's actions for changing this rule. On the left, there's that check mark, which means it's enabled. And then next, we have a LAN firewall. This is typically where you set a lot more rules coming in.
Checkmark means it's allowed.
Checkmark means it's allowed.
I think so.
That probably makes more sense. And X means denied, huh?
Yeah.
Yeah. So yeah, it's not bad. So at the top, we're allowing all traffic for port 443 and 80, which means all of your HTTP and HTTPS traffic, so your internet traffic. And then next you're denying, was that everything?
Yeah.
You're denying everything. And then below that we have default allow and allow for IPv4 and IPv6 for is that outbound going out?
This is LAN.
This is LAN, yeah.
This is
Yeah. But typically the order matters here, doesn't it?
order matters.
Yeah, the order matters for sure because this is an ACL, so it goes down the list. Talk about zero trust.
That's quite the example.
That's quite the example. Yeah, zero trust. Yeah, you just block everything.
I think this is the default pfSense LAN firewall setup.
This is the default.
I
I didn't know
it
that.
is.
That's cool. Kind of to yap around about zero trust though. In enterprise, you usually have like some kind of zero trust architecture, meaning that nothing is trusted and you kind of have to authenticate to everything, just to make sure you don't have some kind of rogue device. Yeah. So now I'm going to talk about competition firewalls. Yeah, Phoenix Flash is broken. That's it. It's stupid. Yeah. So talking about Windows Defender Firewall, I mentioned this before. This is a stateful firewall that uses defined rules. It goes down the list until the packet matches a rule. So it's basically the same concept as an ACL. This is installed on all Windows OSs by default, and you can actually open it on your computer right now if you have a Windows laptop. And you'll see a lot of rules there by default. I believe here the check mark means enabled. Yeah, and then on the right side it's like action. There's like allow or deny. There are specific rules that are there by default that can help you allow certain services. I believe there's one specifically for allowing ping, and I believe it's disabled by default. So I don't think every machine can be pingable by default. So you got to change that rule. And then moving on to IP tables. This is the stateless firewall that has a list of rules similar to the Windows Defender firewall. It keeps going down the list until it matches a rule. This is not some Linux distributions don't have this enabled by default, and you do have to install it. Some other examples of firewalls are UFW, Firewall D, NF tables. What else? I think that's it. That's all the ones we've encountered that I messed it up. Yeah. Sometimes when you install IP tables, it'll automatically override the other ones and disable the other ones for you. What's important to recognize, like if you're just copying onto a machine, what kind of firewall is present, just in case you conflict with it, and then you don't know why your traffic isn't getting through. But there's three chains to IP tables firewall. There's input, forward, and output, as I mentioned before. Each of these has rules, and then they have their default policy. It's important to change your default policy accordingly. You can have like accept and drop, I believe. I think there's block as well, but we don't usually just use drop. I think block tells them that they got blocks, and drop just doesn't do anything to them, right? Yeah, we haven't really used block because it's not important for the red team to know that they got blocked, unless it's personal. Yeah, but we don't really use forward too much because if it's a host-based firewall, you want to mainly manage like input and output. But if there are dependencies, sometimes we do see like forwarding rules to another, so that it forwards traffic to another machine. Does that work with proxies or no? Because like we have Nginx proxy, doesn't that do the forwarding for you? So you don't need a firewall rule for that. You just need input. We got to try that.
Yeah.
That's I just came up with that. It's pretty cool. Oh yeah, UFW and all the other firewalls I mentioned, they are kind of difficult to work with, and we just like to deal with. We just like to pick one and just say like use it across all of them to make sure you don't have to learn everything.
So UFW is too simple. You're not able to specify like, oh, I want it for like this port from this address or this host. And NF tables, or yeah, I think that's newer. And it's essentially an IP tables wrapper, but IP tables should be available for every Linux distro that we encounter.
Yep. So now I want to go into our lab. This is going to be the lab environment that you guys use across the next couple of bootcamp sessions. So it's important that you guys deploy it now. So this is going to be used for our homework today. There's the link there. It's, again, due next week at 5 a.m. But the important thing is that we get everyone to properly deploy a pod and have the environment up before they get out of here. Yeah, make sure you add HTTPS before the camino.sdc.cpp. This is why I pinged you guys yesterday to make sure you have your VPN and SDC accounts prepared so that you can access these resources. But if you have any questions about accessing this, go ahead and let us know. We're going to go around for the next 10 minutes or so to help you guys set up just in case. All right, since we're having some issues deploying your environment, so we can just go over what the homework is. There aren't any questions. So yeah, this just goes over the setup that we went over in the slides. You can revisit this once we do have the ability to deploy our pod. But for this lab, you're just going to be setting up the networking for the three VMs. This involves setting up the router, configuring the WAN IP, going into the pfSense web configurator, And then on each of the Linux and Windows hosts, setting up networking. And then finally checking your one-to-one NAT, just testing if you can actually ping each of the machines. But yeah, you'll just be submitting the deliverable or your documentation. Try to include as much detail as possible, like screenshots, commands you used, and stuff like that, just so that later down the road, if you need to do it again, you can refer to your own documentation. Yeah. Or do we want to just call it there? All right. Yep. Is it this? What is this one? We just switch. Yeah. Well, yeah, that's gonna be it for this meeting. Thank you guys all for coming. Sorry for the difficulties, but if you have any questions, feel free to ask us now or in chat or DM us after the meeting. Next week, we're going to be going into Linux fundamentals
And security.
and security. Yeah. Hopefully, we can get this technical difficulty figured out by Monday or by the end of Monday. Yeah. But thank you guys all for coming.